welcome back to Mathematics Lifeline. In today's video, I'm going to go over two integrals for Calc 2 students who are just learning techniques for integration. So this is going to be sort of a practice video. I'd like you all to try these questions. As you can see, the first one, I'm just looking for an antiderivative, so we need that plus c at the end. And the second one, I'm looking for a numerical value, and I'd like the exact solution for this. But yeah, these are just two questions that we're going to practice here, and I'm going to go through them step by step. So if you'd like, go ahead and pause the video and try these, see if you make any progress, and I'm going to start them right now. All right, so here is the first integral. So hopefully you made some progress on this. I'm going to go ahead and go through it step by step. Now we're looking at this integral and we want to figure out what we want to do with it, right? And your first idea for some of you may have been to do substitution. But if you notice that the bottom function down here has a degree of 3. So if we did a substitution, we would have, an x squared term, and we don't have that in the numerator. So u sub isn't going to work here. What we're going to want to do is partial fractions. So we need to break this up. We need to break the denominator up into 3 factors here that we can use to rewrite this integral. So the first thing we can do is rewrite the integral so that we know we can factor an x out of the denominator here. So that's the first thing we're going to do. So if we factor an x out of x cubed minus x, we're left over with x squared minus 1. So that's a good first step for breaking this down, but we can actually break it down a little bit further because this is a difference of squares. So we can rewrite this integral as 4x minus 2 over x times, well, this is going to break up into x plus 1 times x minus 1 dx. So this is as simple as it's going to get because this is not going to break down anymore. We've got them into linear factors, which is really optimal for partial fractions. Now what we're going to do is we want to rewrite this integral in a way we can actually integrate it. So the way we're going to do that is by breaking it down. So we can say that 4x minus 2 over x times x plus 1 times x minus 1 is equal to sum a over x plus sum b over x plus 1 plus sum c over x minus 1. Now, this is the general practice. We take these linear factors that we have in the denominator, we put them into separate denominators, and we want to solve for a, b, and c because we can actually integrate these much easier. So what we're going to do to solve for a, b, and c is we're going to multiply both sides of this equation by this denominator. So when we do that, we're going to cancel this entire denominator out, so we're just going to have 4x minus 2, and that's equal to a over x times this entire denominator. Well, you see the x's will actually cancel each other out. So we're going to have a times x plus 1 times x minus 1. Now in the b fraction, well, we can cancel out the x plus 1 when we multiply. So we're going to have x times x minus 1. So it's going to be plus bx times x minus 1. And then with the c fraction, we're going to cancel out the x minus 1 term, which means we're going to have cx times x plus 1. So it'll be cx times x plus 1. So now what we can do is we can actually expand this right side in order to solve for a, b, and c. It's going to take a few steps, but we'll get there. So notice that this is the factored form of x squared minus 1. So this is actually the same as a times x squared minus 1. Now everything else we can distribute out pretty nicely. So we're going to say that this is actually equal to, when we distribute a to everything, we're going to have ax squared minus a. Now we're going to move on to the b term. So we have bx times x is going to be a plus bx squared. And then bx times negative 1 is going to be a minus bx. And now with the c, it's going to look very similar. So we're going to have plus cx squared. And then we're going to have plus cx. And remember, this is still equal to this 4x minus 2. 4x minus 2. So now we're going to try to group these terms in terms of what degree of x they're associated with. So as we see, we have ax squared, bx squared, and cx squared. So we can rewrite this as x squared times a plus b plus c. So that's grouping the x squared terms. Now we want to group the x terms. So we can see we can add x times, well, we have a minus bx and a plus cx. So we have negative b plus c. And then the constant term is only this minus a. This is not associated with any x. So what we have is plus, we're going to keep it plus, but it's going to be negative a is our constant. Now, the reason this is helpful is because we can associate this with the 4x minus 2. And we notice that 4x minus 2 does not have an x squared term. So what that tells us is that a plus b plus c should equal 0. Because if this part equals 0, then the x squared term goes away, and we can actually make these equal to each other. So now that we have that, we also know that we want the x terms to match, and we know that we have a coefficient of 4 out in front of here. So that tells us that negative b plus c should equal 4. Because if this is equal to 4, then we have 4x, and that's what we want. And the last one, what we have is negative a, but we want negative a to equal negative 2. This is the only constant term, so we say negative a equals negative 2. So those are three equations that we can use to solve for a, b, and c. So if we know that negative a equals negative 2, this directly will mean that a is going to equal positive 2. Now, if that's the case, then what we have is we have 2 plus b plus c equals 0. And then we also have this negative b plus c equals 4. Now we can go ahead, we can really just subtract this 2 over. So then what we're going to have is b plus c is equal to negative 2. And then we'll have negative b plus c is equal to 4. Now we want to figure out the best way in which we can solve for either b or c. But we notice that if we were to just add these equations together, we can actually cancel out the b term. So we'll cancel the b's and we'll have 2 c's now because we added c and c. And this is going to equal 2, which would imply that c equals a positive 1. So we've solved for a, we've solved for c. Now we want to figure out, okay, what is b? But we know that a plus b plus c should be 0. So we know that 2 plus b plus 1 should equal 0. And if we add the 2 and 1, we get 3, and we can subtract it over. So we'll find that b is equal to negative 3. So we have a solution now for a, b, and c using this partial fractions. So what we're going to do is rewrite this integral in terms of what we have right here. So we can say that this part right here is equal to the integral of a over x, well, a was 2, so we have 2 over x, plus b over x plus 1, well, b was negative 3. So negative 3 over x plus 1, and then we'll have plus c over x minus 1, well, c was 1. So 1 over x minus 1, and all of this should have a dx. Now we can break up this integral so that we can work with it a little bit nicer. So we can say this is the same as the integral of 2 over x dx plus the integral of negative 3 over x plus 1 dx plus the integral of 1 over x minus 1 dx. Now you can evaluate this in any way that you like. The easiest way is probably going to be to do a u sub. But the nice thing about this one is that the u sub is just going to give us a du that's equal to 1. So it doesn't actually affect anything. And these are all integrals that we can evaluate as natural log functions. So the integral of 2 over x is going to be 2 times the natural log of the absolute value of x. Then this one is going to be negative 3, so we're going to have a minus 3 natural log because this x is in the denominator. And because of the u sub is really just going to give us x plus 1 inside. And the last one, kind of the same idea. We're going to have plus the natural log of the absolute value of the denominator, which is just x minus 1. And then don't forget your plus c at the end. So this right here is the antiderivative of this function. And that's all I was asking for here. So we didn't need to plug anything in. Now this question, it's long, but it's really not that hard. And partial fractions can be tricky because a lot of people haven't seen them before calculus. But this is going to be the best way to go about this integral. It's a very systematic way, and in this case, actually the system of equations is very nice to work with, as well as these bottom factors. So yeah, that's it for question 1. I hope you did well on that one. We're going to go ahead and move on to the solution for question 2. All right, so here we have the second question. So hopefully you made good progress on this one as well. So this one we are actually evaluating with bounds on the integral. So we are looking for a numerical value. We're looking for an exact answer here. So what we're going to do for this one is we're going to need to use a trig sub. Now, you may have noticed with this form of the denominator that it's probably going to be a trig sub, and we can't do any u substitution again, because if we did a u sub, our du would be 2x, or negative 2x, and that does not match what we have in the numerator. So we do need to use a trig sub here. So we need to figure out what sort of trig sub we have. Well, we're usually looking at what's under the square root here for these trig subs. So in our case, we have the square root of a squared minus x squared case. Now in this case, what we do is it means we're going to choose x equals a times sine theta as our substitution. So in our case, we have 4 minus x squared. Well, notice this is the same thing as 2 squared minus x squared. So in our case, we're going to say that x is going to equal 2 sine theta. So if x is equal to 2 sine theta, that's good. We know that we need that. We know we need that substitution just because of this general rule here. We want to figure out what dx is, because remember, we're going to trade out all of our x's for 2 sine theta, but we also need to trade the dx. So that's just the derivative. So dx is the derivative of this. Well, that's going to be 2 cosine theta. But remember, we're going to take this with respect to theta. So 2 cosine theta d theta. So this is good. Now that we have this substitution, we can go ahead and break this up into these forms of x's and dx. So our new integral, and I'm going to drop the bounds for this question because we're going to do kind of a lot of work and I don't want the bounds to get a little mixed up. But we're going to go ahead and write this out as the numerator is going to be x squared. So that's going to be 2 sine theta squared over the square root. Well, we have 4 minus x. Well, x is going to be 2 sine theta. So 2 sine theta squared. Now, that's not it because remember, dx is 2 cosine theta d theta. So we're going to multiply by 2 cosine theta d theta. Okay, so this is our new form of our integral. Now, we can actually do a little bit of work with simplifying this here. So what we're going to do is we're going to say that the numerator, well, we have 2 sine theta squared. Well, we can just square the 2 and we can square the sine theta. So we're going to get a 4 sine squared theta. In the denominator, we're going to have the square root of, well, this is going to be 4 minus, and this is the same thing up here. We're going to square the 2, square the sine theta, so we're going to get 4 sine squared theta, sorry. And again, this is still times 2 cosine theta d theta. Okay, now we can do a little bit more because this square root can actually be simplified. So let's write that up here. So the square root of 4 minus 4 sine squared theta. Well, we know this can actually be written as the square root of 4 multiplied by the square root of 1 minus sine squared theta. All I did there was I was able to factor out a 4 from both of these terms. And then because I factored it, I can actually break that into a different square root because the product of 2 square roots is the same as the product inside the square root. So this is going to be, of course, 2. Now, what is the square root? Well, there's an identity that we know that can actually help us out here. We know that sine squared plus cosine squared is equal to 1. And because we know that, we can say that if we subtract sine squared to the other side, we can say that this is actually equal to cosine squared theta. And now, of course, the square root of cosine squared theta is just going to be cosine theta. So we have 2 cosine theta, and that is going to be the simplified version of our denominator here. So what we can do is go ahead and rewrite this denominator. So we're going to rewrite the whole integral now. So we have the integral of 4 sine squared theta in the numerator over, well, in the denominator, we said it was going to be 2 cosine theta when we went ahead and simplified that. So we have 2 cosine theta. And again, we're still being multiplied by 2 cosine theta d theta. But you can see how nice this is now, because at this point, we can actually go ahead and take out 2 cosine theta. They will cancel each other. So then all we have left over is going to be the integral of 4 sine squared theta d theta. And this integral has gotten much nicer. Now I'm going to go ahead and move the 4 to the outside of this function just because I think it's easier to work with it that way. So 4 times the integral of sine squared theta d theta. Okay, so now we've gotten into a much more manageable form. So what we're going to do from here is we're going to try to integrate sine squared theta. And the way we're doing that is we're going to need to use a trig identity. So we know from trigonometry that sine squared theta is always equal to 1 minus cosine of 2 theta divided by 2. So we're going to rewrite this integral like that. So it's 4 times the integral. Well, now sine squared has turned into this. So we're going to have 1 minus cosine of 2 theta divided by 2 d theta. Now we can pull this 2 out and change this into a 2 on the outside because 4 divided by 2. And we'll have the integral of 1 minus cosine of 2 theta d theta. Okay, so now we have it in a form where we can actually integrate this just by using a u sub. Because if we say that u is equal to 2 theta, that means that du is equal to 2 d theta, and that means that du over 2 is equal to d theta. So what that means is we can pull a 2, 1 over 2 out of the function. So we'll cancel with this 2 actually. And we're going to change all of this into a u integral. It's going to be the integral of 1 minus cosine of u du. And this is actually very easy to integrate because this is just going to be u minus sine of u, right? Because the integral of 1 is u and the integral of negative cosine is negative sine. So this is how this works out, but remember that u was 2 theta. So this is going to be 2 theta minus sine of 2 theta. Now, we still are not done because remember we started out in the x world and now we're still in theta. So we need to change these thetas back into something that is in terms of x. Now the problem is we don't really have a good solution for what 2 theta is. You know, we could get there, but getting 2 theta is going to be harder than just getting theta from what we started with. So we can actually rewrite sine of 2 theta. So again, from trigonometry, sine of 2 theta is always equal to 2 sine theta cosine theta. So we can actually rewrite this as 2 theta minus 2 sine theta cosine theta. And now we have everything in terms of just 1 theta. So we want to go ahead and figure out how we can rewrite this in terms of x. Well, here's what we do know. We know that we started out with x being equal to 2 sine theta. And the nice thing about that is that right here, we have a 2 sine theta. So this is just going to turn into an x. Now we need to solve for theta. Well, if we know that x is equal to 2 sine theta, then we can solve for theta by dividing by 2 and then taking arcsine of both sides, which tells us that, I'm going to write it right here. So theta is going to be equal to arcsine of x over 2. We got those just by dividing by 2 and then taking arcsine of both sides. So we have theta is equal to arcsine of x over 2. And that is going to help us with this part. Now the only thing that we don't have is what cosine theta is equal to. So the way we're going to figure that out is by using a triangle. So we're going to set up a triangle for this question. It's going to look like this. Now we're going to choose this side to be x and we're going to choose this angle to be theta because we said that x was equal to 2 sine theta. Remember that sine theta is going to be opposite over hypotenuse. So in our case, sine theta was x over 2, which means the hypotenuse needs to be 2. And then by the Pythagorean theorem, we can say that this side length right here is going to be 4 minus x squared. Because if we were to solve for that side length, we would have to square this side and then subtract off the square of this side and take the square root of it. And that's what we're getting right here. Which tells us that cosine theta is going to be equal to 4 minus x squared over 2. So we can go ahead and write this all in terms of x now. Because we know that 2 theta, well, we said theta was arcsine of x over 2. So we're going to have 2 arcsine of x over 2 minus, well, remember, 2 sine theta was x. So we can say it's minus x times what we said cosine theta was. Well, cosine theta is square root of 4 minus x squared all over 2. And now at this point, we've gotten everything back in terms of x, and we can reintroduce our bounds. Because remember, we were from 0 to the square root of 2 for this question. So now we can go ahead and evaluate after all of this work. So I'm going to go ahead and erase some of this work in the middle so we have a little bit of room here. But we can go ahead and start evaluating. So we're going to evaluate everything at root 2 first. So what we're going to have here is we're going to have 2 arcsine of, well, x is root 2 in the first case, so it's going to be root 2 over 2 minus the square root of 2 times 4 minus the square root, of 4 minus the square root of 2 squared all over 2. That's plugging in the root 2 part of it. Now we want to plug in the 0. When we do that, we're going to have 2 arcsine of 0, because 0 divided by 2 is going to be 0, minus 0 times everything on the inside, so it's root 4 minus 0 squared over 2. So we can go ahead and evaluate this. So the easiest one to see is going to be this one, because this cancels out to 0, and arcsine of 0 is also 0. So this whole right term doesn't even matter. This is all gone. It's all 0. So the only thing that's going to matter for our solution is right here. So we need to figure out what 2 times arcsine of root 2 over 2 is. Well, arcsine of root 2 over 2, however you can think to do that, you can plug it in the calculator, but we can just think about where is sine of theta equal to root 2 over 2. Well, in radians, that's going to be at pi over 4. So we're going to have 2 times pi over 4 minus the square root of 2 times, this square root here is going to turn into 4 minus 2, right? And that's the square root of 2. So square root of 2 divided by 2. And now we can simplify just a little bit more, because this will turn into just pi over 2 minus, when we multiply root 2 times root 2, we just get 2. And 2 divided by 2 is 1, so we get pi over 2 minus 1. And that right there is the answer to this integral. So that is the exact answer of the integral from 0 to root 2 of x squared over root 4 minus x squared. So again, this was a trig sub. It's a pretty tough one, because you do need to use a u sub in the trig sub. You need to know a bunch of these trig identities, right? This is a tough question. So I think it's very helpful to work on this one. Hopefully you were able to get there. If not, that's perfectly fine. Again, trig subs are hard in general, and this is a hard trig sub. But yeah, that's going to be it for this video. I hope you enjoyed it. I hope this helped. If you have any questions, again, feel free to let me know. I will be glad to answer any questions that you have. And I plan on doing more of these practice integration, because I know integration is tough, and I do want to do some more practice videos. So that's all I have for this one, though. I will see you in the next video. Thanks for watching.